The cosmos is an ocean of silent fire and ancient light. Where did all of this come from? This is the ultimate mystery, the question that echoes from our deepest past to the frontiers of modern science. We are going to explore the astonishing idea that the universe was born from nothing, a concept that bends our minds and challenges everything we think we know. By the end of this journey, you will understand the most compelling theories science has for our cosmic origin, from quantum tunneling to the multiverse. We will see how empty space might not be empty at all, and grapple with whether time itself had a beginning. What is your first instinct when you try to picture absolute nothingness? That instinct to ask where it all came from is not new. For as long as we have looked at the stars, we have told stories about where they came from. Long before telescopes and equations, every culture on Earth crafted its own cosmic origin story. These were humanity's first theories of everything, born from wonder and written in myth. Take the ancient Norse. They envisioned the beginning not as a thing, but as a place, a yawning void called Ginnungagap, a silent, misty chasm between the realms of fire and ice. From that emptiness, through a meeting of opposites, the first giant, Ymir, was formed, and from him, the world. On the other side of the globe, Hindu philosophy presented a radically different idea, one that feels startlingly modern. It described a universe that is not born once, but cyclically, breathing in and out over cosmic eons. In this view, creation is not a single event in the distant past, but a recurring rhythm, a dance of manifestation and dissolution that has no ultimate beginning or end. From the aboriginal dreamtime to the Genesis narrative of form emerging from a formless deep, the pattern is universal. Our ancestors, gazing at the same night sky we do, were grappling with the exact same awe and the same fundamental question that drives physicists today. They used the language of gods and giants, of chaos and order, to frame a mystery that simply had no other vocabulary. These myths are more than just folklore. They are profound psychological and philosophical responses to the sheer, overwhelming fact of existence. They tell us that the drive to understand our origins is woven into the very fabric of human consciousness. We have always needed a story for the cosmos, a context for our place within it. Today, we have exchanged the language of myth for the language of mathematics, but the core question remains hauntingly unchanged. How did something, this vast and intricate universe, come from what seems like nothing? This shift from myth to modern science brings us face to face with the real problem, the word at the very heart of our question, nothing. It seems simple, a blank space, an absence. But when we ask if the universe came from nothing, we must first ask, what in the world or out of it are we actually talking about? Our everyday idea of nothing is not nothing at all. Think of an empty room. You walk in and say there is nothing there. But that room is full of space, of air molecules, of light, of the steady pull of gravity from the earth below. It exists within time. That is not nothing. That is a very specific arrangement of something. True philosophical nothingness is a concept that shatters our intuition. It is not an empty box. It is the absence of the box, the absence of space for the box to sit in, and the absence of time in which the box could exist. It means no dimensions, no matter, no energy, not even the empty stage of the universe itself. No quantum fields flickering with potential, no laws of physics to govern what might happen. This is absolute nothingness, a void so complete it is not even a void, because a void implies a container. The ancient Greek philosopher Parmenides wrestled with this over 2,000 years ago. He argued that nothingness is literally unthinkable. To speak of nothing, he claimed, is to speak of something which is a contradiction. How can we conceive of or discuss that which by definition has no properties, no existence, no being at all? Our minds are built to work within a framework of something. We are prisoners of existence, trying to imagine the key that lies outside the prison walls. Modern thinkers face the same dizzying cliff. The physicist Lawrence Krauss famously wrote a book titled A Universe from Nothing, but his definition of nothing is a seething quantum vacuum, a realm of space-time where particles pop in and out of existence. To a physicist, that is the most fundamental nothing we can describe, but to a philosopher that is still very much something. It is an arena with rules and properties. So here we stand at the very first and perhaps greatest hurdle. We are trying to answer a question that might be built on a misunderstanding of its own terms. Is the universe born from nothing, or are we simply unable to conceive of the true, absolute nothing from which it might have emerged? This conceptual minefield is why the question feels so profound and so frustrating. It sets the stage for why any scientific answer feels so revolutionary and so strange, because it forces us to redefine nothing itself. This struggle to define nothing is precisely where science steps in with its most powerful creation story. For much of human history, the universe was thought to be eternal and static, an unchanging backdrop for celestial dramas. Then, in the early 20th century, the cosmic curtain was ripped back. Astronomers like Edwin Hubble, peering through the Great Telescope at Mount Wilson, made a discovery that shattered that eternal stillness. He found that distant galaxies are not just sitting out there, they are racing away from us and from each other. The universe is expanding. This observation, now enshrined as Hubble's law, was the first colossal clue. If everything is moving apart now, then rewinding the cosmic film means everything was once much, much closer together. Go back far enough, and the entire observable universe was compressed into an unimaginably hot, dense point. This is the heart of the Big Bang theory, not an explosion in space, but the rapid expansion of space itself from a state of extreme energy. The evidence for this event is etched into the cosmos. First, there is the afterglow. In the 1960s, two radio astronomers accidentally detected a faint, uniform static coming from every direction in the sky. This cosmic microwave background radiation is the cooled and stretched remnant of the first light that shone when the universe became transparent, about 380,000 years after the initial expansion. It is the oldest photograph we have, a baby picture of the cosmos. Second, the universe's composition tells a tale. The Big Bang model predicted that in those first fiery minutes, nuclear fusion would have cooked the simplest elements, lots of hydrogen, some helium, and traces of lithium. When we look at the oldest stars and distant gas clouds, that is exactly what we find. The observed abundances match the predictions with stunning precision. So the Big Bang is not just a speculative idea, it is a robust framework supported by multiple, independent lines of evidence. It describes the universe's evolution from a searingly hot, dense state to the vast, structured cosmos we see today. But here is the critical and often misunderstood limitation. The classic Big Bang theory takes us to a threshold, a moment of incredible density and temperature, but it does not and cannot take us to the point of absolute nothing. It describes the universe's growth from a seed, but it says nothing about where the seed came from, what happened at time zero, what set the expansion in motion. What existed before that hot, dense state? At that singularity, our equations of gravity break down. The theory hits a wall, leaving the ultimate origin shrouded in mystery. The Big Bang gets us to the very edge of creation, but it stops short of telling us how something emerged from nothing. To cross that final frontier, we need a deeper, more fundamental theory, one that can peer into the realm where time and space themselves were born. The singularity is where our cosmic story hits a wall of pure mystery. Rewind the expansion of the universe, and everything we see condenses into a smaller and smaller volume. The density climbs, the temperature soars. According to the mathematics of general relativity, if you rewind all the way, you reach a moment where the density and temperature become truly infinite. This is the singularity, a point where the curvature of space-time becomes infinite and our most trusted equations simply stop working. They produce nonsense, division by zero, a complete breakdown of predictability. It is the ultimate "here be dragons" on the map of physics. For decades, this singularity was often described in a way that subtly misled our imagination. We pictured it as a tiny, superheated speck of matter, like a cosmic seed, exploding outward into a pre-existing empty void. But that mental picture is wrong. The Big Bang was not an explosion in space. It was the explosive emergence of space and of time itself. That point of infinite density was not a location within a larger arena. It was the moment when the entire arena, the fabric of space-time, came into being. There was no outside for it to explode into and no before for it to follow. This is perhaps the most difficult part to grasp. Our brains are wired to think in terms of containers and sequences. An event happens in a place at a time. But the initial singularity represents the boundary of place and time. It is not an event within the universe. It is the beginning of the universe's very stage. So when classical physics points to this singularity, it is not giving us an answer for how something came from nothing. It is showing us the stark limit of our current understanding, a glaring sign that says, your theory is incomplete here. The singularity is a mathematical cry for help, a signal that we need a deeper theory, one that can handle such extreme conditions and perhaps erase the infinity altogether. To cross this boundary, to ask what happened at or before time zero, we must leave the realm of stars and galaxies behind and descend into the bizarre, counterintuitive world of the very, very small. To cross that boundary, we need a new set of rules. Down at the smallest scales, the universe does not play by the orderly, predictable laws of classical physics. It dances to a far stranger tune, the rules of quantum mechanics. This is the physics of the unimaginably tiny, the domain of atoms and subatomic particles, and it changes everything about our question. At the heart of quantum weirdness is a principle that feels almost rebellious against common sense, the uncertainty principle. In simple terms, it states that certain pairs of properties, like the position and momentum of a particle, cannot both be known with perfect precision at the same time. The more you pin down one, the fuzzier the other becomes. This is not a limitation of our measuring tools. It is a fundamental feature of reality itself. The universe at its core is inherently uncertain, a little bit blurry. This quantum fuzziness has a breathtaking consequence for the concept of empty space. If we try to define a perfect vacuum, a volume of space with absolutely zero energy, we run headlong into the uncertainty principle. To say a region of space has exactly zero energy would require perfect precision, which quantum mechanics forbids. There is always a tiny, unavoidable wiggle room, a fundamental jitter in the fabric of reality. This jitter manifests as quantum fluctuations. Imagine the void not as a still, dark pond, but as a bubbling, frothing sea at the smallest scales. Pairs of particles and their antiparticles spontaneously pop into existence, borrowing energy from the uncertainty of the vacuum itself, only to annihilate each other and vanish back into the background hum an instant later. This happens everywhere, all the time. The space around you right now is teeming with this ephemeral activity, a seething quantum foam. We have even measured the effects of these fluctuations in the lab. They cause tiny, predictable shifts in the energy levels of atoms, and they create a faint pressure known as the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the quantum activity outside them. So the stunning revelation of quantum mechanics is this: what we classically called nothing, the empty void, is not empty at all. It is a vibrant, dynamic medium brimming with potential. The quantum vacuum is not a state of nothingness. It is the lowest possible energy state, a simmering sea of possibility where the laws of physics permit brief, spontaneous appearances of something from what seems like nothing. This completely reframes our cosmic question. We are no longer asking how something came from a true philosophical nothing. We are now asking if our entire universe could be the ultimate quantum fluctuation, a single, spectacular bubble that emerged from the fertile ground of a quantum vacuum and against all odds failed to pop. This quantum foam is the true nature of the void. What we once thought of as empty space is in fact a dynamic medium physicists call the vacuum state. But do not let the word vacuum fool you. It is not empty. It is a seething sea of potential governed by the precise, if bizarre, laws of quantum field theory. To visualize this, picture the fabric of reality not as a smooth sheet but as a restless ocean. Every point in that ocean is a quantum field, an invisible entity that fills all of space. The electron field, the quark field, the electromagnetic field, they are all there, everywhere, at all times. Usually, these fields sit at their lowest possible energy, what we call their ground state. But the uncertainty principle means they can never be perfectly still. They are constantly jittering, vibrating with a faint, irreducible energy known as zero-point energy. This is not energy we can easily tap into. It is the baseline hum of existence itself. Out of this restless hum, temporary disturbances arise. Think of them as tiny, violent waves on that quantum ocean. A sudden surge of energy in the electromagnetic field might momentarily manifest as a pair of particles, a photon and its antimatter counterpart. In the electron field, it could be an electron and a positron. These are virtual particles, and they are not quite the same as the stable particles that make up you and me. They are fleeting borrowings against the cosmic energy ledger allowed by Heisenberg's uncertainty principle. They pop into existence, interact for an almost immeasurably short instant, and then annihilate each other, paying back the energy loan. Physicists diagram these intricate dances using Feynman diagrams, which look like elegant, minimalist sketches with lines and loops. Each line represents a particle's path, each vertex an interaction. These diagrams are not just pictures, they are precise mathematical tools that calculate the probabilities of these quantum events. They map the chaotic choreography of the vacuum, so this vacuum state has very real properties. It has structure, it has energy, it obeys specific physical laws. It is a framework, a stage with its own set of rules upon which the drama of particles plays out. This presents a profound complication for our original question. If we ask whether the universe came from nothing, and we point to the quantum vacuum as that nothing, we have subtly changed the terms. We are no longer speaking of a true philosophical void. We are speaking of a pre-existing arena, a fertile ground brimming with quantum fields and latent energy. The universe would not be emerging from absolute nothingness, but from this rich, dynamic substrate. It would be the ultimate fluctuation, a bubble of true space-time that nucleated within this quantum foam and then, against incredible odds, inflated to become everything we see. The vacuum, therefore, is not the answer to the riddle of something from nothing. It is the bridge that gets us closer, forcing us to ask an even deeper question. What, then, is the origin of the quantum fields and the laws that govern them? Where did this fertile vacuum itself come from? This restless quantum foam provides a startling new possibility for creation. It suggests a mechanism by which our universe could have spontaneously appeared, not from an explosion but through a quantum leap. This process is known as quantum tunneling. In the everyday world, if you roll a ball up a hill, it needs enough energy to reach the top and roll down the other side. If it does not, it simply rolls back. But in the bizarre quantum realm, particles behave differently. An electron confined inside an atom, for instance, can sometimes appear on the other side of an energy barrier without ever having climbed over it. It is as if the ball, without gaining any extra speed, simply vanished from one side of the hill and instantly reappeared on the other. This is not magic, it is a direct consequence of the probabilistic, wave-like nature of quantum objects. There is a small but calculable chance that the particle will simply tunnel through the barrier. Now, apply this wild idea to the cosmos itself. Some theoretical physicists, most notably Alexander Vilenkin, have proposed that our entire universe could be the result of the ultimate quantum tunneling event. Imagine the state of true nothingness or the lowest energy quantum vacuum as a kind of stable valley. An expanding universe like ours, full of matter and energy, would be like a ball sitting on a high plateau. Classically, to get from the valley to the plateau, you would need an immense input of energy to push the ball up the mountain, an event that seems impossible from a state of nothing. But quantum mechanics offers a backdoor. The universe could have tunneled directly and spontaneously from that state of nothing, or a pre-geometric state lacking space and time, into a tiny, inflating bubble of space-time. It did not need to climb the energy mountain, it simply appeared on the other side. In this view, the Big Bang is not a singularity of infinite density, but the moment this newborn bubble of reality began its rapid expansion. The mathematics of this proposal are incredibly complex, involving the wave function of the entire universe, but the core idea is elegantly simple. It uses the established rules of the quantum world to provide a plausible, if highly speculative, pathway for something to emerge from what we might call nothing. It transforms the moment of creation from a singular, inexplicable event into a rare, but statistically possible quantum transition. Of course, this raises as many questions as it answers. What exactly was it that tunneled? What were the laws that governed that transition? The tunneling proposal does not eliminate the mystery of ultimate origins, but it does relocate it. It suggests that the framework for creation, the quantum rules themselves, may be eternal and fundamental, and that within that eternal framework, universes can and do bubble into existence. Our cosmos, then, might not be a unique creation, but simply one that happened to tunnel successfully into a long-lasting, stable expansion. Quantum tunneling offers one path from potential to reality, but perhaps the most elegant attempt to erase the initial mystery altogether came from Stephen Hawking. In collaboration with physicist James Hartle, Hawking proposed a model so radical it aimed to make the question of a beginning simply disappear. Their idea is known as the no-boundary proposal. To grasp it, we must first confront the problem they were trying to solve. Remember that troubling singularity, the point of infinite density where time itself seems to begin. Hawking and Hartle asked, what if that singularity is not a real feature of the universe, but merely an artifact of our mathematics, a sign that we are using the wrong kind of time? In our everyday experience, time is a straight line marching from past to future. We call this real time, but in theoretical physics, there is a powerful mathematical trick where time can be treated as if it were another dimension of space. This is called imaginary time. It is not time you can feel pass, it is a conceptual tool, a fourth spatial dimension used to simplify the ferociously complex equations of quantum gravity. Hawking and Hartle applied this trick to the entire early universe. They proposed that if you trace the cosmos back to its earliest moments, real time does not extend all the way to a sharp, singular beginning. Instead, it smoothly blends into imaginary time. In this model, the universe in imaginary time has no edge, no boundary, no starting point. It is finite in extent, yet completely self-contained. A helpful, though imperfect, analogy is the North Pole of the Earth. Think of the surface of our planet. If you start at the equator and travel north, your latitude lines get smaller and smaller. When you finally reach the North Pole, the concept of going further north ceases to have any meaning. There is no edge there, no cliff you fall off. The North Pole is simply a point on a smooth, continuous surface. Asking what is north of the North Pole is a question that loses its meaning. Hawking and Hartle suggested the beginning of the universe is like that. In their model, if you try to go back to time zero, you find not a singularity but a smooth, curved closure. there is no boundary in space-time, and therefore no moment of creation that demands an external cause. The universe would not have been created from something else, it would just be. It emerges from a fuzzy, quantum gravitational state, a realm of probability where the distinction between space and time blurs away. In this view, the Big Bang is not the ultimate beginning, but more like a transition point, a moment where the universe moved from a quantum realm governed by imaginary time into the expanding, classical universe of real time we inhabit. It is a profoundly elegant idea, suggesting a self-contained cosmos that requires no creator, no prior universe, and no act of creation from nothing. It simply exists, with its history forming a closed surface without a starting edge. Of course, this remains a speculative hypothesis, a beautiful piece of theoretical mathematics that is extraordinarily difficult to test. But its power lies in how it reframes the ultimate question. Instead of asking what came before the Big Bang, the no-boundary proposal implies the question itself might be invalid, like asking what is north of the North Pole. It offers a vision of a universe that is its own origin, complete and entire within itself. Hawking's proposal paints a picture of a self-contained cosmos, one that needs no external ignition. A useful, if imperfect, way to visualize this is to think of a shuttlecock, the kind used in badminton. Picture its rounded, bulbous base. That smooth, curved surface represents the fuzzy quantum beginning in imaginary time, the no-boundary region where our classical notions of a starting point dissolve. There is no sharp edge, no definitive line where something begins. Now, trace your eye upward from that rounded base to where it flares out into the open, expanding cone. That cone is our observable universe, emerging seamlessly from that smooth origin and stretching outward in real time. The entire structure is one continuous, unbroken object. There is no seam where the base is glued to the cone, no moment of assembly. They are fundamentally the same entity, just different phases of its geometry. This elegant image captures the core philosophical implication of Hawking's work. By making the beginning part of a closed, finite geometry, the model attempts to remove the logical requirement for a first cause. In our everyday logic, everything that begins to exist must have a cause. But if the universe does not have a sharp beginning in time, if its history forms a closed surface without an edge, then the question of what caused it may simply not apply. It would be like asking what caused the surface of the Earth to exist. The surface just is. It is a self-contained whole. Of course, this radical idea has faced significant critique from both scientists and philosophers. One major challenge is that the no-boundary proposal, while mathematically beautiful, is extraordinarily difficult to test with observations. It lives in the realm of quantum gravity, a domain far beyond our current experimental reach. Some physicists also argue that the specific conditions it predicts for our universe do not perfectly match what we observe, particularly regarding the patterns in the cosmic microwave background. Furthermore, philosophers point out that even a self-contained geometry in imaginary time might still require an explanation for why that particular geometry exists, rather than some other possibility or nothing at all. The model addresses the origin of our universe within space-time, but it does not necessarily explain the origin of the physical laws that make such a geometry possible. Where do the rules for quantum gravity come from? Today, Hawking's no-boundary proposal remains a respected and influential hypothesis, but it is not the final word. It stands as a brilliant demonstration of how far theoretical physics can go in reimagining our cosmic origins, pushing us to consider that the ultimate answer might not be a dramatic event, but a subtle, seamless transition from potential to reality. It challenges us to accept that the most profound truth about our beginning might be that there was no beginning at all, at least not in the way we have always imagined. Hawking's no-boundary universe is a profound vision of self-containment, but it is not the only path through the quantum fog. Another compelling route was charted by physicist Alexander Vilenkin, who offered a different and in some ways more daring answer. Where Hawking sought to erase the beginning, Vilenkin embraced it, proposing a mechanism for how a beginning could actually happen. His model is known as the tunneling from nothing proposal, and it starts from a more stark premise, a state of literal, absolute nothingness. Not a quantum vacuum, not a fuzzy geometry, but a complete absence of space, time, and physical laws. This is the philosophical nothing we struggled to conceive of earlier, and Vilenkin's mathematics attempts to bridge the unthinkable gap between that and our universe. The core idea relies on that same quantum weirdness we explored, but pushes it to its ultimate limit. In standard quantum tunneling, a particle disappears from one side of a barrier and appears on the other. Vilenkin asked, could the entire universe do the same? In his model, the state of nothing is like one stable valley. A tiny, nascent universe poised to undergo rapid inflationary expansion is like a neighboring valley but separated by an immense energy mountain. Classically, crossing is impossible. Quantum mechanically, there is a tiny, non-zero probability for the entire system to make the jump, to tunnel from the state of non-existence directly into a state of existence. It would not be an explosion in a void, but the sudden, spontaneous appearance of space-time itself already expanding. The mathematics of this involves writing a wave function for the universe, a probability cloud that describes its possible states. Vilenkin found a solution where this wave function could indeed represent a transition from a point of zero size, representing nothing, to a small but finite radius, representing a newborn inflationary bubble. This creates a fascinating contrast with Hawking's vision. Hawking's no-boundary proposal is often described as the universe having no beginning, just a smooth, rounded-off origin in imaginary time. Vilenkin's tunneling proposal gives the universe a definite beginning, a quantum leap from nothing to something. Think of it as two different answers to the same impossible question. Hawking says the universe is like the surface of a sphere with no edge. Vilenkin says it is like a bubble that suddenly nucleated in a sea of non-existence. One avoids a singularity by blending time into space. The other confronts it head-on with a quantum transition from zero size. For decades, these two models have stood as the leading quantum cosmologies for the origin of everything. The debate between them is not just technical, it is deeply philosophical. It asks whether the ultimate nature of reality is timeless and self-contained, or whether it was born in a single, probabilistic event. Both models are speculative, living at the very edge of testable physics, yet they represent our best current attempts to apply the known laws of quantum mechanics to the moment of creation itself. They force us to accept that our universe may not have been inevitable, but could instead be the result of the ultimate roll of the quantum dice, a fluctuation so vast it gave birth to space and time. The quantum dice had been rolled and a universe was born, but this newborn cosmos faced immediate, seemingly insurmountable puzzles. Why does the distant universe look so remarkably similar in all directions? And why is its geometry so perfectly balanced between expansion and collapse? The answers to these mysteries lie not in the main event of the Big Bang, but in a breathtaking prologue called cosmic inflation. Picture the universe in its first fleeting moments, smaller than a single proton. According to the classic Big Bang model, there simply hasn't been enough time for light or any influence to travel from one side of this tiny region to the other. Yet when we look at the cosmic microwave background, the afterglow from 380,000 years later, it is uniform to 1 part in 100,000. How did these far-flung regions coordinate their temperature so perfectly if they were never in contact? This is the horizon problem. Then there is the flatness problem. The universe's geometry is incredibly fine-tuned. For it to have expanded for 13.8 billion years without either collapsing back on itself in a big crunch or flying apart into a thin, cold void, its initial density had to be balanced on a knife's edge of unimaginable precision. It is like balancing a pencil on its tip for eternity. The odds of this happening by chance are astronomically small. In the early 1980s, physicist Alan Guth proposed a radical solution, a cosmic growth spurt of epic proportions. He suggested that in the first tiny fraction of a second, the universe underwent a period of exponential expansion, inflating by a factor of at least 10 to the 26 in less than a trillionth of a trillionth of a trillionth of a second. This idea of inflation solves both puzzles elegantly. The entire observable universe we see today was once a microscopic, causally connected speck before inflation. That tiny region had plenty of time to even out its temperature and density. Then, inflation stretched that speck to a size larger than our entire visible cosmos, taking that smoothness and imprinting it across the sky. As for flatness, think of blowing up a balloon. No matter what wrinkles or curves were on its surface when it was small, as you inflate it to an enormous size, a small patch of its surface appears flatter and flatter. Inflation did the same to the geometry of space, stretching any initial curvature so dramatically that our observable universe appears perfectly flat. But what could possibly power such an outrageous expansion? The engine is thought to be a quantum field, dubbed the inflaton field. Imagine a ball resting at the top of a very gentle, very broad hill in a landscape of energy. This high-energy state acts like a form of anti-gravity, causing space itself to expand at an accelerating, exponential rate. As the inflaton field slowly rolls down this potential energy hill, it drives the relentless inflation. Eventually, it reaches the bottom of the hill, and the inflation period ends abruptly. The enormous potential energy stored in the field is then dumped, reheating the universe into a hot, dense soup of particles, effectively setting the stage for the conventional Big Bang expansion we know. This is the breathtaking link. The microscopic quantum jitters in that inflaton field, the very same kind of fluctuations that make a vacuum froth with virtual particles, did not get smoothed away by inflation. Instead, they were stretched across the cosmos along with space itself. Those tiny quantum wrinkles became the seeds for all future structure, the gravitational blueprints for galaxies, stars, and planets. The pattern of hot and cold spots we see in the cosmic microwave background is a direct fossil of those quantum fluctuations magnified to a cosmic scale. So inflation does more than solve technical problems. It forges a profound connection. It suggests the vast cosmic tapestry we see today, with its great galactic walls and immense voids, has its ultimate origin in the probabilistic, uncertain realm of the quantum world. The largest structures in existence may have grown from the smallest possible vibrations in the fabric of reality at the very dawn of time. Those quantum ripples in the inflaton field were the universe's most important imperfections. As space itself expanded at a dizzying, exponential rate during inflation, it did not stretch these tiny fluctuations smooth. Instead, it magnified them. Imagine a tiny, almost invisible wrinkle on the surface of a deflated balloon. Now, blow that balloon up to the size of the entire solar system. That microscopic wrinkle becomes a vast, rolling ridge stretching across the sky. Inflation did exactly that to the quantum jitters in the early cosmos. It took variations in energy and density that were smaller than a single atom and stretched them across distances larger than our entire observable universe today. In that moment, the probabilistic fuzz of the quantum world was permanently imprinted onto the fabric of space-time, frozen in as the cosmic microwave background radiation we now detect. These stretched fluctuations are not just a fossil, they are the blueprint. Slightly denser regions where the inflaton field had a tiny extra bump meant slightly more gravity. Over the next hundreds of millions of years, that extra gravitational pull acted like a cosmic magnet, gently tugging surrounding matter inward. Dark matter, an invisible form of matter that interacts only through gravity, formed a scaffold first. Ordinary matter, the protons and electrons that would become stars and planets, then flowed into these gravitational wells, what began as a quantum whisper became a galactic shout. The densest seeds grew into the first stars, which gathered into galaxies, and those galaxies into the vast web-like structures we see spanning the cosmos. Every galaxy cluster, every spiral arm, every planet orbiting a distant sun owes its existence to those initial random quantum ticks. This is the profound, almost poetic link. The largest structures we can observe, walls of galaxies hundreds of millions of light years across, have a direct lineage back to the smallest possible vibrations in a quantum field during the universe's first fleeting moments. It means the quantum origin story is not an abstract mathematical exercise. It is written into the very architecture of the night sky. The same quantum rules that allow a universe to tunnel from nothing also dictated the pattern of stars we gaze upon. So when you look up, you are not just seeing points of light. You are seeing the magnified signature of the universe's quantum birth, a frozen moment of creation stretched across the heavens and evolved over billions of years into the rich cosmic landscape we call home. But this incredible inflationary engine might not have stopped everywhere at once. According to some models, the process of eternal inflation could be still happening right now, in a realm far beyond our cosmic horizon, and it leads to a possibility so vast it redefines reality itself. The idea is called the multiverse. Picture our universe not as the entire cosmos, but as a single bubble in an infinite, frothing sea of space-time foam. In the theory of eternal inflation, the inflatoned field, that engine of exponential expansion, does not roll smoothly down its energy hill everywhere. Quantum fluctuations can cause it to get stuck at a high energy point in some regions, even as it falls in others. Where it gets stuck, inflation continues, stretching space at a breakneck pace. Within that ever-inflating background, pockets where the field does finally fall to a lower energy state stop inflating. Each of these pockets becomes a separate bubble universe like ours, with its own Big Bang and subsequent history. Crucially, because the inflating background between bubbles expands faster than the bubbles themselves can grow, these universes are forever causally disconnected. They are islands in an ever-widening ocean, completely unaware of each other's existence, and here is where it gets truly mind-bending. When the inflatoned field settles into a low-energy state in a new bubble, it might not settle into the same valley every time. The landscape of possible vacuum states, governed by the mathematics of string theory or other frameworks, could be unimaginably vast with countless different stable configurations. Each configuration corresponds to a different set of fundamental constants and physical laws. In one bubble, the strength of gravity might be 1,000 times stronger, making stars burn out in an instant. In another, the nuclear forces might be too weak to bind protons and neutrons, so no atoms ever form. Our universe, with its precise balance that allows for galaxies, planets, and life, would simply be one bubble among an infinite number, one that happened to have the right lottery numbers for complexity. This radically shifts the philosophical weight of our original question. We are no longer asking, why does this one universe exist from nothing? Instead, we are asking, why does this one universe have this particular set of physical laws? In a multiverse, the answer becomes statistical. With an infinite number of trials, every possible combination of laws will emerge somewhere. We find ourselves in a universe compatible with our existence because we could not possibly find ourselves in one that is not. This is known as the anthropic principle. It is not an explanation in the traditional sense, but a selection effect. We are here because this bubble allows observers to exist. The stunning implication is that the fine-tuning we see in our cosmos, the seemingly miraculous balance of forces, might not require a fine-tuner. It might simply be the result of a cosmic dice roll in a casino with an infinite number of tables. The multiverse hypothesis is not a proven theory. It is a speculative but logical consequence of extending our best models of inflation and quantum mechanics to their ultimate limits. It pushes the origin story back another step, suggesting that our universe was born not from a singular quantum event in a void, but from a pre-existing, eternal inflationary landscape that continually gives birth to new realities. In this view, the ultimate question of why there is something rather than nothing transforms into a question about the nature of the eternal meta-reality that spawns the endless something of the multiverse. This infinite cosmic froth is a staggering idea, but it does not come without a storm of controversy. The multiverse is not just a scientific hypothesis, it is a philosophical battleground. Its most vocal critics argue it is not science at all, but metaphysics dressed in mathematical equations. The core of their objection is a simple and powerful principle: falsifiability. For a theory to be considered scientific, it must in principle be capable of being proven wrong through observation or experiment. But if other universes are forever beyond our cosmic horizon, causally disconnected from us, how could we ever detect them or gather evidence for their existence? Critics charge that the multiverse makes no testable predictions that are unique to it. Any feature of our universe can be explained away by saying, well, in our bubble it just happened that way. This, they say, moves the goalposts of science into the realm of untestable speculation, a retreat from the hard-won empirical rigor that has defined physics for centuries. It risks becoming a theory of anything and therefore a theory of nothing. Defenders counter that indirect evidence is still evidence. If our best and most successful theories of cosmic inflation and particle physics naturally lead to a multiverse as a consequence, then the success of those underlying theories provides a form of support. They also point to potential, though highly speculative, fingerprints, like the statistical patterns in the cosmic microwave background that could hint at a collision with another bubble universe in the distant past. The debate is fierce because it strikes at the very definition of what science is and what limits, if any, it should accept. This brings us directly to the anthropic principle, the multiverse's most famous philosophical tool. In a landscape of infinite universes with random physical laws, it is no surprise that we find ourselves in one that can support conscious life. We could not possibly be having this discussion in a universe where stars never formed or atoms never stabilized. The anthropic principle is not a causal explanation, it is a statement of observational selection. It says the properties of our universe must be compatible with the existence of observers. For some, this feels like a profound insight, a natural resolution to the puzzle of fine-tuning without needing a designer. For others, it feels like a clever cheat, a tautology that explains nothing. It simply says we are here because we are here. It does not tell us why this particular set of life-permitting laws exists in the first place, only that we had to wind up in a place that allows us to notice them. And this leads to the ultimate haunting question. Does the multiverse truly solve the riddle of something from nothing, or does it merely relocate the mystery? If our universe is a bubble in an eternally inflating meta-reality, we must then ask, where did that inflating background come from? What is the origin of the quantum fields and the laws that govern eternal inflation itself? The multiverse does not erase the need for an ultimate origin. It pushes it back one step from the origin of our universe to the origin of the multiverse generating mechanism. We are left contemplating an eternal, perhaps beginningless, generative process, a cosmic engine that has always been producing reality bubbles. For some minds, this is a more satisfying answer than a singular creation event. An eternal, self-sustaining process feels less in need of an external cause. For others, it feels like an infinite regress, an endless chain of why questions that never reaches a final foundation. The storm over the multiverse reveals a profound truth about our quest. We are probing the edges of knowledge where solid science, daring speculation, and deep philosophy inevitably collide. We are forced to decide what kind of answers we are willing to accept and what mysteries we might have to live with forever. the storm over the multiverse reveals a profound truth about our quest. We are probing the edges of knowledge where solid science, daring speculation, and deep philosophy inevitably collide. We are forced to decide what kind of answers we are willing to accept and what mysteries we might have to live with forever. But what if the ultimate answer lies not in the physics of our universe, but in the mathematics beneath it? This is the promise of string theory, perhaps the most ambitious framework ever conceived. Its goal is breathtakingly simple and impossibly difficult: to weave the four fundamental forces of nature into a single, elegant tapestry. It seeks to unify the gravity that shapes galaxies with the quantum forces that govern atoms, a dream that has eluded physics for a century. To do this, string theory proposes a radical shift in our picture of reality. At the tiniest scales, the fundamental building blocks are not point-like particles, but unimaginably small, vibrating strings. Just as different vibrations on a guitar string produce different musical notes, the different vibrational patterns of these cosmic strings would produce all the particles we see: the electrons, the quarks, the photons, everything. One single type of object vibrating in different ways could generate the entire symphony of the cosmos. This elegant idea, however, comes with a startling requirement. For the mathematics of these vibrating strings to work consistently, they cannot just vibrate in the three dimensions of space and one of time we experience. They need more room. String theory suggests the universe has extra, curled-up dimensions, perhaps 6 or 7 of them, folded into geometries so tiny, 1 billion times smaller than an atom, that we never notice them. The specific way these extra dimensions are folded determines the properties of our reality, the masses of particles, the strengths of forces, everything. And here is where the plot thickens enormously. The number of possible ways to fold these extra dimensions is not just large, it is stupefying. Physicists refer to this as the string theory landscape, a cosmic catalogue of possible vacuum states for the universe. Current estimates suggest there could be 10 to the power of 500 different stable configurations. That number is so vast it defies comprehension. There are more possible universes in this landscape than there are atoms in our entire observable cosmos. Each point in this landscape represents a universe with a completely different set of physical laws and constants. In one, gravity might crush atoms instantly. In another, electromagnetism might be too weak to form chemical bonds. Our universe, with its specific, life-friendly tuning, is just one single point in this unimaginably vast mathematical space. This is where string theory collides spectacularly with the idea of eternal inflation and the multiverse. Think of the eternally inflating meta-reality as a restless, bubbling medium. Each bubble universe that nucleates within it is not just a random fluctuation. It is a crystallization of a specific point from the string theory landscape. As a new bubble forms and inflation ends, the extra dimensions snap into one particular folded shape, locking in that universe's unique set of laws. In this grand synthesis, the multiverse is not just a froth of random bubbles, it is a froth of bubbles, each realizing a different mathematical possibility from the string theory catalog. Our existence here is not just a random quantum accident, but a selection from a pre-existing, eternal realm of mathematical potential. This vision forces us to reframe the ultimate question once more. We are no longer asking why there is something rather than nothing. We are asking why this particular something, this specific point in an ocean of mathematical possibilities, became real. The answer may lie in the chaotic process of eternal inflation, randomly sampling the landscape, or perhaps in deeper principles we have yet to uncover. It suggests that the bedrock of reality is not physical stuff, but mathematical structure, and our universe is one verse in a nearly infinite poem of possible forms. String theory's landscape of possibilities is vast, but what if our universe's story is not a single verse, but a stanza in an endless cosmic poem? This is the heart of cyclic models, a radical alternative to a singular beginning from nothing. These theories propose that our Big Bang was not the ultimate start, but merely the latest chapter in an eternal cycle of cosmic death and rebirth. Instead of a universe born from absolute nothingness, we get a universe endlessly transforming from one state of existence into another. One of the most famous of these ideas comes from the renowned physicist Roger Penrose with his conformal cyclic cosmology. Penrose's vision is both elegant and mind-bending. He suggests that the distant future of our universe and the earliest moments of a new one are, in a specific mathematical sense, identical. As our cosmos expands forever, all matter eventually decays or gets pulled into black holes, which then evaporate via Hawking radiation. After an almost unimaginable span of time, the universe becomes a vast, cold sea of massless particles like photons and gravitons. In this state, the concept of scale loses all meaning. A universe stretched to infinite size and a universe compressed to a single point become mathematically indistinguishable. This is the conformal symmetry, a reset button on size and distance. At this point of infinite expansion, which Penrose calls the eon, the universe can seamlessly connect to a new Big Bang, starting the cycle anew. The evidence he points to are strange, circular patterns in the cosmic microwave background, which he interprets as gravitational wave imprints from collisions of supermassive black holes in the previous eon. While controversial, the idea paints a hauntingly beautiful picture, a phoenix universe rising from the ashes of its own infinite expansion. A very different kind of cycle emerges from string theory, known as the ekpyrotic or cyclic model, proposed by Paul Steinhardt and Neil Turok. Here, the drama plays out in a higher dimensional space. Our three-dimensional universe is envisioned as a three-dimensional membrane, or brain, floating in a bulk dimension alongside another brain. These two parallel worlds are drawn together by a force, then collide. That collision is the Big Bang, a release of immense kinetic energy that heats and populates our brain with matter and radiation. The brains then bounce apart, expand, cool, and empty out over trillions of years, only to be drawn together again for another collision, another bang. In this model, each cycle is not a perfect repetition. The collisions could introduce slight variations, so each new universe might have slightly different properties, evolving over endless cycles. This framework elegantly addresses the horizon and flatness problems without needing a period of inflation, replacing it with the slow, gentle approach of the brains before their fiery embrace. Both of these cyclic visions fundamentally change the philosophical stakes. They remove the need for a creation event from absolute nothing. The question transforms from why is there something rather than nothing, to why is there this eternal cycle of transformation. The universe in these views simply always was, not as a static entity, but as a perpetual engine of renewal. It offers a kind of cosmic immortality where an end is always a prelude to a new beginning. Yet even these models have their own frontiers of mystery. What set the cycle in motion in the first place? If there was no first cycle, does an infinite past make logical sense? And what is the nature of the higher dimensional arena in which the brains dance, or the mathematical framework that allows for conformal resets? Cyclic models do not so much solve the riddle of origins as they reframe it into a deeper, perhaps even more profound, eternal mystery. Cyclic models offer a universe of eternal return, but they still operate within a framework of time. This leads us to the most disorienting frontier of all, the nature of time itself. Did time have a beginning, or is it an eternal river flowing from an infinite past? The answer is not just about clocks and calendars. It strikes at the very core of our cosmic origin story. According to Einstein's theory of general relativity, space and time are not separate stages upon which the universe plays out. They are woven together into a single dynamic fabric called space-time. Matter and energy tell space-time how to curve, and that curvature tells matter how to move. This inseparability means you cannot have space without time or time without space. They are a package deal. So when we trace the expansion of the universe back to the Big Bang, we are not just tracing matter getting denser. We are tracing the fabric of space-time itself shrinking to a point. At that theoretical singularity, the equations tell us that both space and time would have zero extent. They would cease to exist as meaningful concepts. This is why many physicists argue that the question, what happened before the Big Bang, might be as nonsensical as asking what is north of the North Pole. On the surface of a globe, the North Pole is the point where all lines of longitude converge. The concept of north simply loses its meaning there. In the same way, if time itself began with the Big Bang, then the word before refers to a time that did not exist. It is a grammatical ghost, a question that presupposes a framework that wasn't there. This is not just a clever semantic trick, it is a direct implication of our best theory of gravity. If the universe's history is a film reel, the Big Bang would be the first frame. Asking what is on the reel before that first frame is a logical error because the reel itself starts there. Some models, like the Hartle-Hawking no-boundary proposal we discussed, take this idea and run with it. They replace the singular beginning with a smooth, rounded-off geometry in imaginary time, a domain where our everyday notion of sequential time does not apply. In that fuzzy quantum origin, there is no clean line between before and after. There is just a transition from a timeless state of potential into the flowing time we experience. Think of it like the moment water freezes into ice. As liquid, the water molecules move freely in time. When they crystallize into ice, a new, rigid structure emerges with different properties. The moment of crystallization is not a moment in the liquid's time, it is the beginning of the solid's ordered state. Similarly, our arrow of time, with its clear past, present, and future, may have crystallized from a timeless quantum soup. This perspective forces a profound philosophical shift. If time is not an eternal backdrop but an emergent property of our universe, then the cosmos did not come from something in time. It came with time. The totality of existence includes its own beginning as part of its structure. The universe does not sit in time. Time is contained within the universe. This makes the idea of a creation event from nothing feel slightly less paradoxical, because there was no pre-existing time in which a creator could have acted, or a cause could have preceded its effect. The universe, in this view, simply is, complete with its own starting point woven into its fabric. Yet the human mind rebels. We are storytelling creatures wired for narrative, for cause and effect. The idea of something, especially everything just being, with no prior cause, feels like an intellectual dead end. It challenges our deepest intuitions about how reality must operate. We are left staring at the edge of understanding, wondering if the ultimate answer to our existence is not a dramatic story of creation, but a silent, self-contained fact, a geometric and quantum reality where the question of origin finally dissolves into the stillness of a timeless beginning. That silent, self-contained fact might be more than geometry. It could be mathematics itself. This is the startling claim of physicist Max Tegmark and his mathematical universe hypothesis. It proposes a radical answer to our ultimate question, one that dissolves the distinction between the physical world and the abstract realm of numbers and equations. Tegmark suggests that our physical reality is not just described by mathematics, which is undeniable, but that it is mathematics. In this view, the universe is not a thing that obeys mathematical laws, it is a mathematical structure, period. Think of it like a triangle. The idea of a triangle, with its three sides and angles adding up to 180 degrees, exists independently in the abstract world of geometry. It has properties and relationships that are timeless and necessary. When you draw a triangle in the sand, you are not creating the concept of a triangle. You are creating a physical representation, an instantiation of that abstract mathematical object. Tegmark argues our cosmos is the same. The mathematical structure that describes all particles, forces, and the fabric of space-time does not merely model the universe, it is the universe. The physical stuff we see and feel, from stars to our own thoughts, is just a kind of shadow, a concrete manifestation of an underlying abstract form. This flips the entire origin story on its head. If the hypothesis is true, then the universe did not come from anything physical, like a quantum vacuum or a previous cycle. It exists because the mathematical structure that corresponds to our particular cosmos exists in the landscape of all possible mathematical structures. Its existence is not contingent on a physical creation event, but on the logical necessity of its own mathematical coherence. The question, why is there something rather than nothing, transforms into a very different one. Why is this particular mathematical structure realized or instantiated as our experienced reality? This leads us into deep philosophical waters. In the vast set of all possible mathematical structures, most would be chaotic, barren, or inconsistent. They would not support complex, self-aware substructures like us. Our specific mathematical universe, with its elegant laws allowing for stars, planets, and consciousness, is a very special one. Tegmark posits that perhaps all mathematical structures that are logically consistent actually exist in some reality. This is the ultimate multiverse, not of bubbling space-times, but of every possible abstract mathematical form. Our universe is simply the one we find ourselves in, because we are a self-aware pattern within its specific mathematical relations. We could not perceive a universe built on contradictory axioms. This idea blurs the line between physics and mathematics until it vanishes. It suggests that the ultimate bedrock of reality is not made of tiny strings or quantum fields, but of numbers, sets, and symmetries. The laws of physics are not rules written by a creator. They are the inherent properties of the structure itself, as intrinsic to it as three sides are to a triangle. While this is a profoundly elegant and intellectually daring vision, it is also intensely speculative and controversial. Critics argue it is untestable, pushing science into the realm of pure metaphysics. They ask, what does it mean for a mathematical structure to be real, and why should the abstract existence of a structure necessitate a physical experience of it? Yet, the mathematical universe hypothesis forces us to confront the uncanny effectiveness of mathematics in describing the cosmos. It offers a breathtakingly simple, if deeply strange, answer to the ancient mystery, a universe that is because it mathematically must be. The mathematical universe hypothesis dissolves physics into abstract form, but another path seeks to solve the mystery by rebuilding physics from the ground up. This is the quest for quantum gravity, a theory that would finally marry the vast cosmic scales of general relativity with the probabilistic weirdness of the quantum world. One of the most promising and profoundly different approaches is called loop quantum gravity. Instead of imagining tiny vibrating strings, loop quantum gravity takes Einstein's insight that space-time is a dynamic fabric and asks, what is that fabric made of at the smallest possible scale? The answer it provides is startling. Space itself is not smooth and continuous, but woven from tiny, finite loops of gravitational field, a literal fabric of reality. These loops form a network, a spin network, and the geometry of space emerges from how these loops are connected, much like the pattern of a tapestry emerges from woven threads. This granularity of space has a dramatic consequence. There is a smallest possible unit of volume, a quantum of space. You cannot divide space infinitely, just as you cannot divide a piece of cloth beyond the individual threads that compose it. This fundamental graininess changes everything about the beginning. In Einstein's classical theory, you could squeeze the universe into an infinitely dense point, a singularity. But in loop quantum gravity, you cannot squeeze space past its smallest possible volume. As you rewind the cosmic expansion and approach that extreme density, the quantum nature of gravity itself becomes dominant. Here, the equations of loop quantum cosmology, a simplified application of these ideas to the whole universe, reveals something extraordinary. The attractive force of gravity, which pulls everything together, is overwhelmed by a powerful quantum repulsive force generated by the granular structure of space itself. Think of it like compressing a spring. At first, it gets easier to push, but at a certain point, it resists with tremendous force, wanting to bounce back. The universe, in this view, hits a quantum spring. Instead of collapsing into an infinite singularity, it reaches a maximum density and then bounces, beginning a new phase of expansion. This is the Big Bounce. It suggests our Big Bang was not the absolute beginning, but a turning point, a cosmic rebound from a previous phase of contraction. Our expanding universe may have been preceded by a great cosmic crunch, where a prior universe collapsed in on itself, only to be saved from oblivion by this quantum gravitational repulsion, springing back out as the universe we inhabit today. This creates another compelling cyclic model, but one driven by quantum physics rather than colliding brains or conformal resets. The universe transitions through endless cycles of expansion, contraction, and bounce, a cosmic heartbeat echoing across eternity. The profound implication is that our universe likely did not emerge from absolute nothingness, but from the quantum gravitational transformation of a prior state of existence. The question of ultimate origin is pushed back from the birth of our universe to the potentially infinite cycle of bounces that may have always been. While still a theoretical framework, loop quantum cosmology offers a tangible, physics-based alternative to the singularity, painting a picture where the universe is not born from nothing, but eternally reborn from itself, thanks to the unseen, granular threads from which space itself is woven. This granular, bouncing cosmos forces us to confront a deep-seated assumption, one wired into our brains since we first observed the world. Every effect has a cause. A ball moves because it was kicked. A tree grows from a seed. This principle of causation is the bedrock of our understanding, the logic we use to navigate reality. So when we ask where the universe came from, we instinctively seek a cause, something outside of it that set it in motion. But here lies the philosophical earthquake. If the universe is the totality of all space, time, matter, and energy, then what could possibly exist outside of it to serve as a cause? Can the principle of causation, a rule we derived from observing events within the universe, be applied to the universe as a whole? This is not a new puzzle. In the 18th century, the Scottish philosopher David Hume launched a devastating critique of our naive understanding of causation. He argued that we never actually observe a cause. What we observe is constant conjunction. We see event A, then event B repeatedly. The sun rises and then it gets light. We call the sunrise the cause of the light. But Hume pointed out we do not perceive any necessary connection between them. We only infer it from habit. Our belief in causation is a psychological expectation, not a logical certainty we can prove. This skeptical view shakes the foundation of our cosmic question. If causation is not an iron law of reality, but a useful pattern we observe within reality, then we may be making a profound category error by demanding a cause for reality itself. The universe might not need an external cause in the same way a painting needs a painter, because the painting exists within a framework of space, time, and causality that the universe itself provides. The canvas cannot demand an explanation from outside the frame if the frame is all that exists. Modern philosophy and physics have wrestled intensely with this. Some argue that the principle of sufficient reason, the idea that everything must have an explanation, still applies. They contend that even the totality of space-time requires a reason for its existence, whether that reason is a necessary being, a multiverse generator, or a set of eternal mathematical truths. Others, however, find compelling the idea of a causally self-contained universe. This is precisely what models like the Hartle-Hawking no-boundary proposal or eternal inflation suggest. In a self-contained quantum cosmology, the universe does not have a cause that precedes it in time because time itself is part of the package. The universe is not an effect within a chain, it is the entire chain. Its explanation is internal, found in its own geometry, its quantum laws, or its eternal cyclical nature. It simply exists as a brute fact. This does not feel satisfying to our cause-seeking minds, but that may be the point. Our intuition was forged in a middle world of medium-sized objects moving at slow speeds. It may be spectacularly ill-equipped to handle questions about the origin of everything. The search for a first cause might be like a character in a novel searching for the author of the book, not realizing that both the character and the story exist within a different logical framework. We are left with a haunting choice. Do we hold firm to the causal principle and insist on an explanation outside the cosmos, even if that leads to an infinite regress or an uncaused cause? Or do we accept that at the ultimate scale, the rules change and the universe might be its own reason for being, a self-explanatory loop in the fabric of existence? Our search for a first cause leads us down a path humanity has walked for millennia. Long before equations and quantum fields, the most enduring answer to the origin question was not a theory, but a presence, a creator. The theological perspective offers a resolution that feels intuitively satisfying to many, directly addressing the causal chain our minds instinctively construct. This is the classical cosmological argument often associated with philosophers like Thomas Aquinas. Its logic runs clear and deep. We observe that everything within our experience, every event and object has a cause. A tree comes from a seed, a building from a blueprint and labor. If this chain of causes cannot go on infinitely backward, there must be a first cause, an uncaused cause that set everything else in motion. This first cause, the argument concludes, is what we call God, a being whose nature requires no prior explanation, who exists necessarily. This God is conceived not as another item within the universe, but as the ground of all being, existing outside of time and space, the source from which time, space, and matter themselves flow. In this view, the Big Bang is not a spontaneous quantum event, but the moment of divine creation, the initial act that brought the physical framework into existence. The universe, then, is not self-contained, it is contingent, utterly dependent on this necessary being for its very existence. This framework provides an elegant answer to the problem of infinite regress and satisfies the deep human longing for ultimate purpose and design. It transforms the question from a cold scientific puzzle into a matter of profound relationship and meaning. Yet, this perspective stands in stark contrast to the scientific models we have explored. Those models, from quantum tunneling to eternal inflation, strive for a completely naturalistic explanation, one that operates within the laws of physics without invoking a transcendent agent. They seek to show how the universe could arise from its own internal logic, from a quantum vacuum or a mathematical structure requiring no external push. The central tension lies in the very definition of nothing. For the theological view, true nothingness is just that, a complete absence from which only a transcendent power could summon something. For many scientific models, the fertile nothing of the quantum vacuum or the eternal landscape of mathematical forms is sufficient. One posits an uncaused cause outside the system, the other seeks a self-causing mechanism within the system's own rules. This brings us to a fascinating and perhaps unbridgeable interface, the theological concept of God as a necessary being existing outside of time is a philosophical answer to a logical puzzle. It intentionally places the explanation in a realm beyond scientific inquiry, a realm that by definition cannot be measured or tested. Scientific cosmology, on the other hand, by its very nature, attempts to explain the universe using principles we can, at least in theory, describe, quantify, and potentially observe. When science proposes a universe with no temporal boundary, like the Hartle-Hawking no-boundary proposal, it is offering a self-contained account that makes the question of a prior cause irrelevant. From a theological standpoint, one could argue this simply describes how God created a universe without a beginning in time, crafting a reality that is, from its own internal perspective, eternal and self-sufficient. The two narratives operate on different planes, answering different kinds of questions, one of purpose and ultimate cause, the other of mechanism and physical law. They are not necessarily contradictory, but they speak different languages. The conflict arises when either side claims its domain provides the only valid kind of answer. For the scientifically minded, invoking a creator can feel like giving up on the search, inserting a mystery in place of an explanation. For the theologically minded, a purely materialistic origin can feel like a story missing its most essential character, the author. This age-old dialogue does not resolve our mystery, but it beautifully frames the human condition. We are creatures who observe effects and seek causes, who perceive design and yearn for a designer, yet who are also driven to understand the machinery of reality on its own terms. Whether one finds the answer in a necessary being or in a necessary mathematical structure, the quest itself reveals our profound need to find a story for our existence that makes sense of the breathtaking fact that we and all of this are here at all. This dialogue between disciplines reveals a landscape of profound questions, not a single, simple answer. If we could gather a quantum cosmologist, a philosopher, and a theologian in one room, we might be surprised by their common ground before their inevitable divergence. All three would likely agree that the classical Big Bang singularity, a point of infinite density, is an unsatisfactory end to the story. It is a mathematical signal that our understanding is incomplete, a placeholder for a deeper truth. They would also concur that the question itself, why is there something rather than nothing, is perhaps the most profound one a conscious mind can ask. It is the ultimate mystery that has animated human thought for as long as we have looked at the stars. Where they diverge is in their tools, their definitions, and where they are willing to place the final period in the sentence of explanation. The quantum cosmologist points to the equations, to the fertile quantum vacuum, or the self-contained geometry of a no-boundary universe. For them, the answer lies in a naturalistic mechanism, a process that, however strange, operates within a framework of physical law. The cause of the universe is internal to its own logical and mathematical structure. The philosopher steps back, scrutinizing the very language of the debate. They challenge the cosmologist's definition of nothing, pointing out that a quantum vacuum with properties and potential is still something. They question whether our principle of causation, derived from within the universe, can be applied to the universe as a whole. The philosopher's role is to guard against logical overreach, to remind us that an elegant mathematical model does not necessarily answer the deeper metaphysical why. The theologian, listening, offers a different kind of resolution. They argue that an infinite chain of physical causes, whether bouncing universes or bubbling multiverses, still requires an ultimate, uncaused reality to ground it. For them, the intricate fine-tuning and the very existence of contingent being points toward a necessary being, a reality whose essence is existence itself, standing outside of space and time as its source. This is not a conversation where one side must defeat the others. It is a necessary triangulation of human understanding. Science provides the breathtaking how, the detailed narrative of cosmic evolution from the first fraction of a second to the present day. Philosophy provides the critical framework, clarifying the questions and examining the limits of our concepts. theology addresses the ultimate why, engaging with purpose, meaning, and the possibility of a transcendent ground. A complete picture of our origins may require holding these perspectives in tension, recognizing that each illuminates a different facet of the same dazzling, incomprehensible gem. The mystery of existence sits precisely at this fertile intersection. To ignore any one voice is to risk an incomplete story, whether it is a story without mechanism, a story without logical rigor, or a story without a sense of ultimate wonder. Perhaps the most honest answer we can give right now is that the universe invites us into a lifelong conversation, one where the search itself, across all these disciplines, is a testament to the curious, yearning nature of the very consciousness the cosmos somehow produced. That conversation across disciplines is not just theoretical, it is actively driving the most ambitious experiments in human history. Today, we stand at a remarkable frontier where these grand ideas about the universe's birth are being probed not just with philosophy, but with telescopes, satellites, and detectors of exquisite sensitivity. The quest is to move from beautiful speculation to hard evidence, to find the fingerprints of creation etched into the fabric of reality. One of the most promising hunts is for a specific kind of ripple in the oldest light we can see. The cosmic microwave background, that baby picture of the universe, is not perfectly smooth. It has subtle patterns of hot and cold spots, which we call polarization. Scientists are meticulously searching this polarization for a particular twist, a curling pattern known as B-modes. These are not caused by matter, but by something far more profound, the stretching of space itself during the inflationary epoch. If inflation truly happened in that first unimaginable fraction of a second, it should have sent powerful gravitational waves, ripples in space-time, racing through the infant cosmos. Those waves would have left a distinctive swirling imprint, a B-mode pattern, on the cosmic microwave background. Finding this signal would be like discovering the fossilized shockwave from the Big Bang's prologue, direct evidence for inflation and a glimpse into the energy scales a trillionth of a second after whatever beginning occurred. Experiments like the Simons Observatory in Chile and future space missions are scanning the sky with ever greater precision, hoping to catch this whisper from the dawn of time. It is a painstaking search, as the signal is incredibly faint and easily confused with dust in our own galaxy. But the potential prize is nothing less than a validation of our most successful cosmic origin story. Meanwhile, the quest to understand quantum gravity, the realm where these origins truly reside, is advancing on other fronts. Since we cannot recreate the conditions of the Big Bang, physicists are turning to nature's own laboratories, black holes. A black hole's core is a singularity, a point of infinite density where our laws of physics break down, mirroring the conditions of the cosmic beginning. By studying how black holes form, evolve, and potentially evaporate through Hawking radiation, we are indirectly probing the laws of quantum gravity. The information paradox, the puzzle of what happens to information that falls into a black hole, forces us to reconcile quantum mechanics with gravity in new ways. Insights from this cosmic puzzle might illuminate how space and time themselves emerged from a quantum state. Remarkably, we are also building analogies for these extreme physics here on Earth. In labs, scientists use ultra-cold atoms arranged in lattices or carefully arranged materials to simulate the behavior of space-time. These analog gravity experiments allow researchers to study phenomena like Hawking radiation in a controlled setting, offering tangible clues about how quantum fields behave in curved space. It is a testament to human ingenuity, using tabletop experiments to explore the physics of the most violent events in the cosmos. The excitement is palpable because the tools at our disposal are becoming revolutionary. The James Webb Space Telescope is not just showing us stunning images of galaxies. It is peering back to the universe's first billion years, studying the formation of the very first stars and black holes. This helps us understand the initial conditions that emerged from the Big Bang. Meanwhile, a new generation of gravitational wave detectors, like the planned Laser Interferometer Space Antenna, or LISA, will listen for the collisions of supermassive black holes and possibly the cosmic gravitational wave background, a steady hum from the early universe that could carry signals from inflation or other exotic processes. Each observation is a potential clue, a piece of the puzzle that could confirm one model, rule out another, or, most thrillingly, reveal something entirely unexpected. We are living in a golden age of cosmic detective work, where the next major discovery could come from a telescope's new dataset or a theorist's brilliant calculation, finally shedding light on the deepest darkness the moment our everything began. From ancient myths of cosmic giants to the equations of quantum gravity, our journey has spanned the breadth of human wonder. We have seen the solid ground of the Big Bang theory give way to the quantum precipice, where time and space themselves become fluid. We have stood before the elegant visions of Hawking's self-contained universe and Vilenkin's quantum leap from nothing, wandered the infinite landscapes of the multiverse, and pondered the mathematical fabric of reality. Each theory is a towering achievement of human intellect, a story woven from the threads of observation, mathematics, and sheer imagination. Yet, for all this brilliance, a definitive answer remains just beyond our grasp. The question, was the universe born from nothing, still echoes unanswered in the silent spaces between our equations. It endures as one of science's greatest and most humbling mysteries. And perhaps that is where its true power lies. This unanswered question is not a failure of knowledge, but the very engine of discovery. It is the spark that ignites our curiosity, driving us to build ever better telescopes, to conceive ever deeper theories, to peer into the void and demand a story. In seeking our origin, we are not just solving a puzzle, we are forging a connection. We are the universe becoming conscious of itself, trying to trace the contours of its own birth. That quest, that relentless need to understand where we came from, is what binds us to the stars and to each other. It transforms the cosmos from a distant spectacle into a home we are desperately trying to comprehend. So, what do you think after this journey through the possibilities? Where does your mind settle? Do you find a self-contained cosmos more compelling, or a single, probabilistic quantum birth? Share your thoughts on this ultimate question below. The conversation itself is part of the great, ongoing story of discovery.